This video is about finding limits analytically, or some authors will call it algebraically, and we're in the context of the topic of limits within calculus. This is not the first video in the series, but it's going to use and depend on some things we've already seen with them, including notation and definitions and limit laws and things. Now, for our notes, we'll say this: just as important as knowing how to apply various algebraic or analytical methods for finding limits is knowing when to apply them. The following outline, though not necessarily exhaustive of all possible cases, can assist in getting familiar with when to apply appropriate methods. That's kind of the key here. And so I would highly recommend writing this out with your own hand and then using it as you practice limit problems. It's in the form of an outline so that it's kind of like a decision tree that you can apply to any limit problem. We always start at the top, and the first thing we try is direct substitution, and that's just plugging the value that x is approaching in for x in the function. Now, if we do that and get a real number, then we're done. That is the value of the limit. That's the easiest case, which is why we try it right away. But of course, sometimes it doesn't work where we get a real number. So if we get a over 0, where a is not 0, some non-zero number over 0, then we're going to use deduction to determine the result being either positive or negative infinity. There's an entire video on that process, but we'll see it in some examples here as well. If we get 0 over 0, thirdly, this is called an indeterminate form. So we're going to try several things in this case. That means it's not enough to determine what the limit is. It may exist, it may not, we just don't know yet. So we'll try several things in these cases. We'll try to use algebra tricks like factoring, expanding, simplifying, reducing, all the good old algebra that I'm sure you're familiar with at this point. Secondly, we might need to rationalize a numerator or denominator. That's another algebra trick. Thirdly, we may need to simplify a complex fraction. Okay, so at this point, if you're reading through this list, you now know why you had to take pre-calc or college algebra, because that's exactly what we're doing in this context here. Fourthly, we may need to use trigonometric identities. Okay, that's why you need to know trigonometry. And if those are a little rusty, you can brush them off. You'll get a chance to practice them as we go through examples here. Or we may need to use the limit laws or properties we've already stated in this context of limits. Or we may need to split an absolute value into a piecewise form. And again, we've seen all these things happening so far. So that's the case of getting 0 over 0. That's one indeterminate form. But it's also possible that we might get infinity over infinity. And this is also called an indeterminate form. It's just a different kind. And in this way, we're going to multiply by a convenient form of 1. That's what we could say is involved when you rationalize a numerator or denominator, or this other trick, which would involve dividing all terms by the highest power of the denominator. And so this list of steps to find limits analytically is broad, and it will cover many sections and examples. I'm putting the whole list here, even though we may not get to some of these last cases until a little bit later on, but having the whole list written out once as one place to go for all your limits will, I think, become a good habit and resource for you. Importantly, let's note the following. We will eventually come to something you may have heard about called L'Hopital's rule. Students love this rule. Until then, we will get good at these methods listed above and avoid using it. Okay, so for good reason. A lot of people like L'Hopital's rule because eventually, when you get into some more applications of limits, which we haven't quite seen yet, it turns out to look a lot easier than some of these methods. The problem is L'Hopital's rule does not always work as we would love it to. And in many cases, we actually have to start our limit evaluation process by using any of these methods and kind of keep L'Hopital's rule as a last resort. We will eventually get to it. Let's now try some examples where we want to find each limit analytically. And our first example is the following. We want to find the limit as x approaches 2 of, now we have a rational function in parentheses here. The numerator of it is x squared minus 2. The denominator is x cubed minus 3x plus 5. and all of that is squared outside those parentheses holding that rational expression. So there's our function. Now we're going to practice utilizing the steps we wrote directly above. And so can you find the top of the list and what the first step is? You got it. We're always going to try direct substitution first, because if it works, it's the easiest step or method to find the limit. So when we say try direct substitution, we're going to take our function given as x squared minus 2. I'm going to write that as blank squared minus 2. And then in the denominator it was x cubed, so I'll put blank cubed. And then minus 3x is minus 3 blank plus 5. So now we have blanks where all the x's are in our function. And what we're going to do is take the value that x is approaching, so in this case x was approaching 2, and we're simply going to plug it in for all these blanks. We're substituting the value x is approaching in for x. Now, as you may note in our outline above, if this simplifies to a real number, we're done. We have the limit, which is why we always check this first. But it may or may not work that way. Let's see. In the numerator, we have 2 squared minus 2. Well, that's really 4 minus 2, which is 2. In the denominator, we have 2 cubed minus 3 times 2 plus 5. Well, that's really 8 minus 6 is 2 plus 5 is 7. And also, let's not forget, this entire expression was squared. Ooh, it's easy to forget those squareds there. So we have to make sure we square this result. Okay, so we ended up with 2/7. But if we square that, we'll end up with 4 over 49. Of course, that is a real number, and so we're done. That's the limit. Yes, finding a limit can be that easy. Of course, it's not always, but if direct substitution gives you a real number, you're done. Let's try a second example. This one reads, we want the limit as x approaches 4 of a rational function where the numerator is x squared plus 3x and the denominator is x squared minus x minus 12. Okay, so we go to the top of the list every time. Let's try direct substitution and see if that will be as easy as our first example here. We're going to try plugging in 4 for all these x's. Well, that would give us 4 squared plus 3 times 4 in the numerator. And then down below, we have 4 squared minus 4 minus 12. Okay, if we try to simplify this, the numerator, let's see, that's 16 plus 12, so 28. And in the denominator, we have 16 minus 4, which is 12, minus 12, which is 0. Uh-oh. Okay, so 28 over 0 is the result of our direct substitution. But if you look back at our outline, that means we have to do a little more work. We can't call that an answer. Well, we can get a hint to the answer, but it's not quite finished yet. So in this case, where we have some non-zero number, 28, over 0, we want to analyze this using the deduction process we've also learned in limits. So in deduction, as you may recall, we often want to utilize a number line and put the value that x is approaching on it so we can analyze what's happening to each piece of this function, the numerator and denominator. But you'll also recall that when you have a function, a rational function like this, if it's simplifiable, that usually makes our work easier. So let's go ahead and just simplify. I think we can do it here. We have x squared plus 3x in the numerator over x squared minus x minus 12 in the denominator. But those seem probably factorable. Look at the numerator. If you take out an x, you'll be left with x plus 3 after it. In the denominator, this is probably factorable as well. We'll have x and x in the front of each binomial, and then probably a minus 4 and a plus 3. You can double check with some factoring methods on that. It should work. And notice these x plus 3 factors cancel, which simplifies, which means our function is really x over x minus 4. And that will actually help simplify our analyzing process. Remember that in this problem, x is approaching 4, and it does not specify from one specific side, which means we assume it's from both sides. So our analysis really does have to be from both sides. I'm going to throw in some values surrounding 4. So 3 to the left of it, 5 to the right of it. And let's take a look at our numerator and denominator as they kind of creep through those values, getting closer to 4 from both sides. So I'm going to use pink for our numerator. As we walk closer to 4, remember, you can start as far to the left and right as you'd like. Yes, eventually to the left, you'll be in negative value territory. But if you're approaching 4, you're eventually going to get right up close to it where we're looking here, zoomed in. So eventually you're going to walk your way all the way up past 3, 3.5, as you're getting closer to 4. Notice those values for this numerator are just x. Well, those are the values on the number line, which means that's going to be positive for sure. So the numerator, when approaching 4 from the left, is positive. Now, let's also consider the numerator when approaching 4 from the right. So this would be walking in from 5 down to maybe 4.5, 4.25. I mean, you name it. You're getting closer to 4, walking toward it from the right side as you're approaching it. We're doing from both sides here. But notice those values will always be positive as well. So it appears that if we're approaching 4 from both sides, the numerator is positive either way. So let's kind of keep that note. Let's consider the denominator. We'll use a turquoise color for this. And if we approach 4 from the left with our denominator, so this is us walking all the way up through eventually 3, 3.5, and so on. Notice we're plugging those x values in for x in the denominator, but since those values are smaller than 4, if you take away 4 from them, as our denominator specifies, x minus 4, then you're going to get a negative value for it. So interestingly, our denominator is negative as we approach 4 from the left. Now let's look at the denominator as we approach 4 from the right as well. So again, we're walking down from 5, 4.5. We're getting closer and closer to 4 from the right. But notice those values are all greater than 4. And when you plug them into this denominator expression of x minus 4, something greater than 4 minus 4 will still be positive. All right, let's try to summarize all this information here. There's quite a bit on here. If we look at approaching 4 from the left, we did that now both with the numerator and denominator. The numerator is in this pink color. It was a positive. Denominator is negative. If you take what we know about the deductive process, the combination of those opposite signs means that this function would be approaching negative infinity as x approaches 4 from the left. Okay, now look to the right of 4. As we approach 4 from the right, notice the numerator and denominator were both positive. So again, going back to our deduction process, that means the function would be approaching positive infinity. But if we bring that together with this function overall, from where we started here, if the function is approaching negative infinity on one side and positive infinity on the other, that means, I guess you could say graphically speaking, that means there's a vertical asymptote right at 4, and this function is going, let's see, down to the left of it and up to the right of it. If you think back to some graphical examples we've seen, because it's going to opposite kinds of infinity, which means that overall we'd have to say that this function's limit does not exist. There's not even one symbol that could summarize these two different infinities that we're approaching. So we just say dne for this result. Let's try a third example. This one is the limit as h approaches 0 of the following expression. It's a rational expression where the numerator is the quantity 2 plus h in parentheses cubed minus 8. The denominator is just h. All right, well, we've been using x a lot lately. The fact that this one uses h doesn't really change anything. It's just a different letter, but everything will work the same way. So we're going to try direct substitution first, as our outline would state, because again, if we get a real number for this, then we're done. So we're plugging now in 0 for h. So I'm going to rewrite this as, instead of 2 plus h, I'll have 2 plus 0 cubed minus 8 in the numerator. And then down below, h is just plugged in as 0. Okay, notice what happens here though. If I go to the numerator, 2 plus 0 is 2. 2 cubed is 8. So really I have 8 minus 8, which is 0 in the numerator. But of course we have 0 in the denominator. Okay, so let's think about what's happening here. If you go back to our outline, 0 over 0 is a particular kind of answer, it means we actually cannot determine this limit from what we have so far. This is one of our indeterminate forms where we have to try something else. If you go way back up to our list, our outline of steps, when we get 0 over 0, we had a whole bunch of things we can try. And so given the way that this problem is set up, we're going to see which one of those might apply. You'll notice the numerator has this 2 plus h cubed. That might be some reason to say maybe we can expand, maybe try to expand and simplify the numerator. So let's try this. Now, one thing to be careful of, when you're rewriting this, it's easy to be used to the algebra where you simply just rewrite the rational part. But until we're actually done with the limit, we're going to keep copying LIM with what the variable is approaching. So I'm going to rewrite this problem as limit as h approaches 0. Then I'm going to recopy this rational expression, but I'm going to start working on expanding this 2 plus h that's cubed here. So I'm going to write it as 2 plus h times 2 plus h times 2 plus h. That's, after all, what that means. Of course, then we're subtracting 8, and this is all over h. Now, we know that direct substitution doesn't do us any good on this. We already discovered that. So we're just going to expand this algebraically and see if that gets any better for us. In the numerator of this limit, which I'm going to recopy, so I have limit as h approaches 0 of, notice I could take a pair of these binomials 2 plus h and FOIL them together. It doesn't really matter which pair, just for style. I'm going to keep the first one as just 2 plus h. And then I'm going to take these second two binomials and FOIL them out. That would give us a 4 plus 4h plus h squared. If we FOIL those together, then I have this minus 8, and this is all still over h. Okay, so algebraically we'll keep going. I'm going to rewrite this again. We have the limit as h approaches 0 of. Now in this numerator, I'm going to distribute this first binomial, 2 plus h, into this new trinomial we got in the previous step. So I'm going to distribute the 2 to everything and then the h to everything. Okay, it's just ugly. Just kind of hold your nose, take an algebra pill, and go for it here. So 2 times 4 is 8, 2 times 4h is 8h, and then 2 times h squared would be 2h squared. Going back through now to distribute the h, we'd have plus 4h plus 4h squared plus h cubed, and don't forget the minus 8 that is hanging on the end up there. And this is all still over h. Okay, so algebraically it almost looks worse at this point, but notice there's a little bit of simplifying we can do. In the numerator we have an 8 and a negative 8 on the ends that we could actually just cancel right out. So let's go ahead and rewrite again. We have the limit as h approaches 0 of this numerator, but now those 8's are gone, so the numerator is really just 8h plus 2h squared plus 4h plus 4h squared plus h cubed all over h. Okay, and if you try direct substitution now, it's actually not quite fixed yet. We would still get 0 over 0, which makes us a little sad because we're not quite out of that problem yet. But notice now algebraically that the numerator terms all have a common factor of h. So what I can do is rewrite this all yet again. So I have the limit as h approaches 0, where in the numerator I'm going to factor out an h from all the terms. That would leave us with an 8 plus 2h plus 4 plus 4h plus h squared. And then I still have this h in the denominator, but now these h's, the one I factored out of the numerator and the denominator, would cancel, which actually eliminates our problem here. So all we have left is the limit as h approaches 0 of what's left in the numerator, which is 8 plus 2h plus 4 plus 4h plus h squared. To evaluate the limit at this point, again, we just try direct substitution until it works. And if it doesn't work, we keep trying algebraic tricks here. But now notice if I plug in 0 for h in all these terms that have an h, they would turn to 0, which means I have 8 plus 0 plus 4 plus 0 plus 0. And of course, this turns out to be a real number. 8 plus 4 is 12. As soon as you get a real number with direct substitution, you're done. That means this limit value is 12. So notice that's why we have to call this form that we initially had indeterminate when it was 0 over 0. There was not enough information to determine at that point what the limit was. After all of our algebra headache, finally at the end, we took care of our problem, eliminated the 0 over 0 by canceling these h's, and turns out we got a nice real number out of it. Let's try a fourth example. This one reads, the limit as h approaches 0 of, it's a fraction where the numerator is the quantity 3 plus h in parentheses, all to the negative 1 power, and then minus 3 to the negative 1 power, and then that's all over h. Now, this form can be deceiving. In fact, it's probably best to rewrite this knowing the algebraic property of a negative exponent from algebra class. We can rewrite this as the limit as h approaches 0 of, in this numerator, instead of putting 3 plus h all to the negative 1 power, we can write that as 1 over 3 plus h. That's equivalent. And then instead of minus 3 to the negative 1, I could call that 1 over 3. That's just using the negative exponent understanding or rule there. And it's all still over h. Well, if you try direct substitution here by plugging in 0 for h, in the numerator you're going to get 1/3 minus 1/3, which is 0, and the denominator you get 0. Again, 0 over 0 is a problem motivating us to do more. This is an indeterminate form. So we're going to go to the list we have in our outline above to see what might work here. You may recall from algebra class that this expression is actually what you call a complex fraction. And you can simplify a complex fraction as one of our methods above. So let's rewrite this as the limit as h approaches 0. And now, to simplify a complex fraction, actually are a couple different ways you could do it. One way would be to multiply the top and bottom of this fraction by what sometimes is called the minor LCD. That is, if you look at each of these terms, they all have a denominator, a little one in terms of font size. So like the 3 plus h, the 3, and then beneath this h is actually a 1. So the minor LCD of all, the LCD of all those denominators would be 3 times 3 plus h. If I multiply the numerator and denominator each by that, then it should simplify according to ways to simplify complex fractions. This is not the only way to do it. If you have a preferred way that's different, that could be fine too. In the numerator, if I distribute this minor LCD to both terms, the 3 plus h will cancel, giving me just a 3. In the second term, the 3 will cancel, giving me, notice there's a minus between them, but then I'd have this 3 plus h left. So my numerator now is 3 minus the quantity 3 plus h in parentheses. Then below, I'll have 3 times h times 3 plus h. Now, if we simplify, remember we're trying to get out of our problem, which was an indeterminate form here, and we're just trying one of the tricks listed in our outline above to do so. If we keep going algebraically, I'll rewrite this as limit as h approaches 0. Remember, do not forget to copy down this LIM with h approaching 0. It's really easy to forget that, but it's worth points. You can lose them for not having that because that is very much a part of the problem until we actually evaluate the limit. Now, in our function, if we look at the numerator, we can distribute this negative sign to the 3 plus h we have from our previous step, which actually gives us 3 minus h, also known as negative h. And then down in the denominator, we have this 3 times h times 3 plus h. But now notice what's going to happen. These h's will cancel, that is, the h in the numerator and the h in the denominator that's outside of the parentheses will cancel, which simplifies this to be the limit as h approaches 0 of really just a negative 1 in the numerator now over a 3 times a 3 plus h. But now if I plug in 0 for direct substitution for h, I really have negative 1 over 3 times 3, which is, in other words, -1/9. And we have a real number there, which means finally we evaluated a limit. Let's consider a fifth example. This one reads, the limit as t approaches 1 of the following function. The numerator is t to the fourth minus 1. The denominator is t to the third minus 1. Of course, you'll try direct substitution right away, but it won't be too hard to figure out that this one will turn into 0 over 0, which is an indeterminate form, which motivates us to try something else. It does not give us an answer. If you go up at our outline, where we have all our various methods to try listed out, I would say in this case, if you remember back to algebra class, this might be a good one to try factoring. These original numerator and denominator are factorable. So let's go ahead and rewrite this as the limit as t approaches 1. We keep rewriting that every time. And then let's factor the numerator, which is a difference of 2 squareds. It would turn out to be t squared plus 1 times a t squared minus 1. But then even the t squared minus 1 could be factored further. That's really t plus 1, t minus 1. So I'm going to rewrite it that way right where we are here. T plus 1, t minus 1. Okay, so the original numerator of t to the fourth minus 1 has now been fully factored into t squared plus 1 times t plus 1 times t minus 1. If we look at the denominator, originally it was t cubed minus 1. That's actually a difference of cubes. So yes, you have to know all your factoring at this point. That would be factored into a t minus 1 in parentheses times a t squared plus t plus 1. And so now after factoring, you can see, as was the case even back in algebra class, that you have a common set of factors that'll cancel. These t minus 1s, we have one in the numerator, one in the denominator, and since everything is factored, we can cancel those, which means this is really the same as the limit as t approaches 1. We're just recopying everything now, where now the numerator is just the t squared plus 1 times a t plus 1, and the denominator is this t squared plus t plus 1. There's no need to expand the numerator now to get back to some, combined terms expression. Doesn't matter. You can leave it as is and try direct substitution. I think it'll work fine. If you look at the numerator, this would be really a 1 plus 1 in the first binomial, which is 2 times 2. So really 4 is the numerator if we direct sub here. And then down below, if you plug in 1 for t, you have 1 plus 1 plus 1, which is 3. So it looks like 4/3 is our real number answer. And as soon as we get to a real number, we're done. Let's try a sixth example. This one is the limit as x approaches -4 of the following function. The numerator is the square root of x squared plus 9, that's all under the root, and then minus 5, all over x plus 4. Now, of course, try a direct sub right away. You might get lucky, probably not. If you try plugging in -4 for x here, you'd end up with the square root of 25, which is 5 minus 5. That's really 0 in the numerator, and then down below, of course, 0 as well. So again, we have another indeterminate form. This should motivate us to try something else. Now, out of all the methods listed in our outline above, notice we've already done stuff like factoring, simplifying complex fractions. This one may fit a different method, which is, let's try rationalizing. Go back up and look at those methods. We can rationalize sometimes a numerator, sometimes a denominator. In this case, it's the numerator we might want to rationalize given that it already has the radical expression up there. So let's go ahead and try rationalizing by rewriting this as the limit as x approaches -4. I'm going to copy down the original function for a second here. This is the square root of x squared plus 9 and then minus 5, and the denominator is x plus 4. Now recall, to rationalize an expression like this, you have to multiply by the conjugate, and we want to rationalize the part that has the radical expression, so the numerator in this case. The conjugate of that numerator would be the square root of x squared plus 9 plus 5. You simply change the sign between the terms. Of course, this is really multiplying by 1, so we have to copy that directly down below. Square root of x plus 9, square root of x squared plus 9 plus 5 also getting multiplied by our denominator here. Let's take this down another step. I'm going to recopy as the limit as x approaches negative 4. Now in the numerator, when I multiply by foiling these two expressions together, the original numerator and this new conjugate numerator, first times first would turn out to be just an x squared plus 9. Outer times outer and inner times inner, as you may recall, when you're rationalizing, will always cancel. So you don't even have to rewrite those. Outers and inners cancel, but then last times last would be a minus 25. So really we have x squared plus 9 minus 25 in our numerator. And then down below, this is a perhaps ugly looking conundrum here. We have x plus 4 in our original denominator. We're trying to multiply that by the conjugate of the numerator, which is this, square root of x squared plus 9 plus 5. Instead of foiling that together, we're actually going to try for now just leaving it kind of as is. I'm going to put x plus 4 in parentheses, and then I'm going to copy down this conjugate after it. So square root of x squared plus 9 plus 5. Okay, because I think we're going to see a convenient something to do with that in a second. Instead of trying to expand it, it's easier just to leave it. Let's keep going by rewriting yet again. We'll have the limit. Keep copying the limit as x approaches negative 4. This time now in the numerator we have x squared, and then we had plus 9 minus 25, so really that's x squared minus 16. The denominator we had x plus 4 times the square root of x squared plus 1, x squared plus 9 plus 5. Okay, now it's still not looking great, and you can always keep trying direct substitution at any of these steps to see if you've fixed the problem yet. But as you'll note, even if you tried it right now, you would still get 0 over 0, which means we're still sad. We haven't quite fixed our problem yet, so we keep going. Now notice this numerator of x squared minus 16. That is a difference of two squares. So let's try factoring that out, which means now we have the limit as x approaches negative 4 of this numerator could be written as x plus 4 times x minus 4. That's factoring a difference of squares. And then down below, we're just going to copy the x plus 4 times this ugly root, square root of x squared plus 9 plus 5. And now you can finally see why we would have kept or wanted to keep the denominator as is, because now these x plus 4s can cancel since everything is factored. And now we can try, well, let's rewrite one more time. We have the limit as x approaches negative 4. Now in the numerator we just have x minus 4. In the denominator we have the square root of x squared plus 9 and then plus 5. Let's try direct substitution now and see what happens. We're plugging in negative 4 for x. In the numerator that would give us a negative 8. In the denominator I'd have, if I plugged in negative 4, let's see, 16 plus 9 is 25 in the square root, so 5 plus 5, which would be 10. Of course, you can reduce this. Negative 8/10 is really just negative 4/5. But that is a real number, which is what we were looking for, which means finally we have the limit. Let's try a seventh example. This one is the limit as x approaches 0 from the right of 1 over x minus natural log of x. Now, if you were paying attention carefully in previous videos in this series, you may have already seen this exact problem, but I wanted to throw it in here in the context of our analytical process for finding limits, where we know now all the limit laws, we have the outline. We want to be able to apply the outline and get to an answer on a problem like this. So notice, if you're approaching 0 from the right, that matters, and we can use some deduction possibly on that. But let's also recall that with our limit laws, if we have two different terms here, like two functions, as we do, we can split this up and make it the limit as x approaches 0 from the right of the first term, that's 1 over x, minus the limit as x approaches 0 from the right of the second term, which is just the natural log of x. So this is a limit law. If you go back and review those, you'll see, I think, pretty clearly which one it is. We can now explore these. Now, deductively, we could handle this first one. If you think of, okay, a graph is kind of a shortcut to the deduction here. If you think of the graph of 1 over x, It has a branch in the quadrant 1 and quadrant 3. Okay, and so when you're approaching, as x is approaching 0 from the right, that means you're walking down the number line towards 0 from the right. That means you're in this upper branch where the values are increasing. In fact, they're chasing a vertical asymptote as you go up, which means this would be a positive infinity for that result, that term limit. In the second term here, the limit as x approaches 0 from the right of natural log of x, again, we'll just kind of pull out the graph here and recall the graph of natural log plummets down toward a vertical asymptote on the y-axis. And so as x approaches it from the right, these values start to plummet downward forever, which means that limit result is negative infinity. And so as we saw actually already with this example, this is really infinity plus infinity. Remember, infinity is not a number, but we can kind of treat it as one. It works the same way with these negative signs here. Negative, negative. Infinity is really positive or plus infinity. And if you add infinity to infinity, you get, well, infinity and beyond, I guess. So infinity is our result for this limit. Remember, that doesn't actually exist, but describing it as infinity tells us how it doesn't exist. That means it increases without bound if it's positive infinity.